Okay, so yeah, basically I was saying, I'll do that again. If you go to Arizona Data Science Institute, click on education, go to the AU Arizona Data Lab. This is the workshop series. Click on cracking the coding interview and scroll down. You can see there is a wiki page where I have been updating all the video recordings and the whiteboard which we used. So let's look at the whiteboard from last week. Okay, so this is last week, maybe was it Wednesday? Maybe. Yeah, so I know we started looking into dynamic programming, and I said there are a couple of terms that's associated with dynamic programming, like overlapping subproblems, optimal substructure, etc. Then we realized that optimal substructure is another word for recursion, and overlapping subproblems is what we saw earlier, which is to find the answer of 4, we need the answer of 3 and 2, but 2's Fibonacci is again calculated twice, so we are trying to avoid that. And we saw that the optimization one is we first wrote the whole thing in recursively, and this was it, like Fibonacci of n-1 plus Fibonacci n-2. And then we realized that this is very inefficient. So we decided, okay, let's add an optimization, which is a cache, also known as memoization. So in this, all we did was we created a new cache or new array of cache of size 100. And then we started asking the question, if the value exists in cache, return it. If not, initialize it with fib of n-1 and fib of n-2, and that's it. Okay, so now the second optimization is let's do it iteratively, which is nothing but we take the whole thing here and we just, instead of a recursion, we will write it as, maybe we did not touch it last day. Maybe I'll start with that too. Or maybe we did. That's fine. Only host can share. Still, I am the host. Click on participants. Nope. Security share screen. Content. You cannot start sharing when somebody else is sharing. So let's check it. In the coding interview. Nice. We have it here. What is the right? Same page. We look at time complexity. We wrote this in recursive form, and optimization 2 is what we were at, I think. So let me start with that, if I can find where my pencil is. Okay, so optimization 2, or let me actually do it this way, use a different color so that this can be explicitly said that, so this is a solution. So remember, the first thing we did was, the very first thing we did, the solution is recursion. Jesus. How do you move back? Because it's 2 fingers. Okay, great. So use another solution 0, right? Solution 0 is a perfectly valid solution for the given problem, but it's not, it's valid, it'll work, but it's highly inefficient. So which is why we went to optimization 1 or solution 1, which is let's add a cache. Then the next thing is we go and we add another optimization. So let me delete this line. Let's call it optimization or solution 2, which is, let's rewrite the whole thing iteratively. 1 second, it is making me Apple Pencils allowed to draw. There you go. Okay. So, no, window, this window, yes, okay. Yeah. So the difference is, because it's the same function, we are going to do exactly same as before, which is we will write everything as it is. Only difference is in this case, this won't be recursive, but we will still be using a cache. So let's start the whole thing. We'll start with static int cache equal to new int new int let's say of 100. And then let's call it inside the public class main. This is where we are initializing it. Then we have a function main. Public static int main and do it the right way so that my brain is tickled. Static main. We have string args. Start here. First thing we do is we fill up the whole cache with -1 for I is 0, I less than cache dot length. I plus plus, we are going to say cache of I equals -1. Now, the only thing left is for us to write the function, which is, let's call it same thing as Fibonacci, public static. What did we do? I don't know. There's always, I don't know what the output is. That's okay. Fib. We're taking int n, integer n. Only thing I want to do this time is I want to, earlier when the first thing we did was if cache of n not equal to -1. That's exactly what we did. So we will return cache of n. Okay, you'll also do the same thing, which is if n less than or equal to 1, cache of n is equal to n. So in short, we are doing cache of 0 is 0 and cache of 1 is 1. Else what we do is same thing, but this time instead of calling it recursively, we just use another for loop for int is equal to 2. We'll start from 2. I less than cache dot length. I plus plus, and all we are doing is cache of I is equal to cache of I minus 1 plus cache of I minus 2. And that's it. After this, all we have to do is return cache of n, whatever value is here. So remember, the very first few steps we always try is we are doing one, paraphrasing a problem. Then we do the core logic, which usually branches into, in this case, it is branched to recursion. And we also look for edge/null cases. Then we do a dry run with one value. Then we do it online editor. And since it's only class 5, we are still using online GDB. Once we get to class 15, we'll start using lead code itself. So now using online GDB and writing it in Java is going to force us to deeply embed in our head that, okay, this is int. I have to remember this is int. Because we will see that once we slowly start switching to Python, your brain will automatically ask, wait, this was supposed to be int, right? So and that question you will end up asking the interviewer. Anyway, so we did this, we did paraphrasing. We are at the recursion. So we decided, okay, we're not going to use recursion. So we are going to use iteration this time. And in iteration, we think we got the core logic right completely. Edge and null cases. So we are taking care of the n less than or equal to 1. So those are the edge, and those are null cases. We might also want to ask the interviewer if n, what is the maximum value? And he says n is greater than 10 power 5. Then we do a print error and return. Right. So this is your null check, which so what is called edge cases. Right. You might have to add that at the end. I'm not giving too much importance to it. Let's go and try with the dry run. So we dry run, we are going to start. So another color. Let's start with, oh, what is this? So now we have the answer coming naturally. We are returning an int. And in this function here, in the main, we are going to, sorry, that's just realized I wrote inside here. So let's do it legally itself. We are gonna call if n greater than 10 power 5, system dot out dot print ln error and return 0. And then remember, we are inside the main. We haven't yet called, we do int out equals fib of, currently let's use 4 or something, right? And we can do system dot out dot print ln out. So this is done. We're closing the main function. We are inside fib. Let's start with 1. Let's start initially with 0. 0 goes inside, comes here. So let's say this is fib of 0. Fib of 0 comes in here. Is cache not equal to -1? No, this is not there. Is n less than or equal to 1? Yes. So cache of n is 0. So cache of n now looks like this. We have cache of n, which is supposed to have 100 data points, of which 0 is here. And then we come return cache of n. So 0 gets returned back to the user. So let's do ask fib of 1. 1 comes here. Is the cache? No, the cache is not there. Okay. Return cache of n. So we probably won't even need this eventually when we get to only the full-fledged iteration, because if we know the cache is not going to be empty, not going to have a value unless we fill it up. But we'll keep that, because if let's say this thing was inside a for loop and you want to check for int, whatever, let's say we are giving it an array, right? If it's 1, 2, 3, 4, and the first value will get stored as cache of n, so it's okay to leave that there for later. Anyway, coming back to our point, 1, this is not there. Okay, is this there? Yes. So we're going to fill this up with 1 and return the value as of now 1. So we get out was initially 0. Second case out is 1. Let's try 2. 2 comes here. 2 comes here. It's not available. So we can go into n less than or equal to 1. No. So for int I is equal to 2, I less than cache dot length I plus plus, which probably we shouldn't even do that, right? We should actually use cat. See, when we do dry run, see how I'm finding my own mistakes. Less than n, right? So when we do 2, starting at 2, is it less than or equal to n? Yes. I plus plus. So cache of 2 is going to be cache of I minus 1, which is cache of 1, which we know is here, is 1, plus cache of 0. In this case, is 0. Okay, so then we found another mistake, that we should not have initialized cache of code is equal to, then it should be back to 1, right? Because remember, in Fibonacci, we want, how does it go? Was it 0 or 1? I don't even remember. 0, 1, 1, maybe it was 0, right? So 0, 1, 1, 2, 3. Okay. If it's 0, 1, 1, a very, very simple, easy way to do this is, even before we come inside, we'll hard code this value, right? So let's call this.
Yeah, it's 0, 1, 1.
0, 1, 1, right? So, okay, that's okay. In that case, we'll do just cache of 0 is 0, cache of 1 is 1. We will do cache of 2 is 1. Maybe cache of 2 is natural, right? So we don't have to do that. So we'll just do only this part, no more confusions. We'll come here, cache of 1, 2. So we are back to passing. We all assume we did 0, 0, 1, 1, and now we are coming in and asking for 2. 2 is I is equal to 2, I less than or equal to n, which is 2 again. So we will have exactly one value. Cache of 2 is equal to 1 plus cache of I minus 2, which is 0. Right? So now our cache is getting filled, where in our new cache we have 0, 1, and 1. index y 0, 1, 2, 3. Let's say the next question is fib of 3. 3 comes all the way here. I'm going to fill it up again. So remember, this is an optimization you can think of eventually. This, if you are coming in every time and running this whole for loop, which is why I was saying, if you are eventually thinking of sending that in an array, we can reuse the same cache. But that, okay, let's not think about that. This is optimization, what we call that optimization solution 2. Okay, so now for 3, we realize cache of 3 is equal to cache of 2 plus cache of 1, which is cache of 2 is 0, 1, 2. There we go. Sorry. 3, this is 2. The cache of 3 is equal to cache of I minus 1, which is cache of 2, which is 1, plus 1. And that's why the third Fibonacci value is 2. Okay, all good. So you see how I'm going with that, right? So even if you stop here, you are done. Your answer for dynamic programming is done. This is, in fact, dynamic programming is one of the best questions to show your knowledge. Starting from recursion, you started by adding a memoization, then you added an iteration, and you can even tell the interviewer that at this point, yeah, we can add more optimizations by not having to do this I is equal to 2 every single time, and etc. etc. So this is good. This is good enough solutions. And in fact, in this particular case, there is one more solution we can do. Do you know what that is? Like, let's say, I'll give you a hint. It doesn't have for loop. Well, it has, okay, no, never mind. It has a for loop, but we are not using a cache. So remember, our first solution was recursion, memoization, iteration. So first solution was yes, recursion, no memoization, no iteration. Second solution was yes, recursion, we use memoization, not iteration. Third solution was we used yes, memoization, yes, iteration, no recursion. Fourth solution is we can do it even much more efficiently by not using recursion, not using memoization, but only using iteration. Do you know how to do that? Solution 2. Let's call this solution / optimization 3. And you must remember, this can be done only for this example. It might not work for every other example. So usually your thought process should be, let's start writing with recursion. Let's add memoization in. Now let's bring it to iteration. And you leave it open, mostly saying, hey, what more can I do? And in this case, another thing you can do is by removing the memoization itself, right? But if you start doing 1 to 3, you're still having a good answer, and that's good. It's a perfect solution for dynamic programming. Okay, so what do you think is the good solution for this, where we are not using memoization?
We can have two variables like previous and current. We can have a for loop.
Okay.
Previous is initially assigned to 0. Current is 1.
Nice.
And in the for loop, starting from 2 to n plus 1 or
Or less, all right.
yeah, equal to n, we will have previous is equal to current. So yeah, previous is equal to current. Oh, this is so we'll save the value of current in a temp.
Okay.
Yes, and previous is equal to temp, and current is equal to current plus previous.
Okay, so let's take an example. We'll start with 2. We come here. Temp value is, let's temp current
Sorry, I'm
previous.
sorry to interrupt. Like, temp will be previous. Sorry, temp is equal to previous. We saved the previous because we are overwriting it, and previous is equal to current. And
Temp is equal to previous.
yes,
Okay.
and previous is equal to current.
Previous is equal to current.
Current is equal to current plus temp.
Current is equal to current plus temp. Okay, so that's
Yeah.
correct. Current plus temp. Okay.
Yes. Mm.
Let's take an example and try it out. So we come in for, let's say we're coming in for 2. We have temp. We have previous. We have current. 2 comes in. Temp is equal to previous because initially when we come in, the value of previous is 0, current is 1, and temp doesn't exist. And then inside the for loop, we start here, we say temp is previous, 0, previous is current, 1, and current is current plus temp, okay, 1 plus 0. So now we are filling it, so what are you returning? So is this what do you
Oh,
return at the end?
um, in the end, we will return current.
Perfect. Now, if my number was 2, we finish there and we return the value 1.
Yes.
Let's go back. If the second number is 1, yes, 0, 1. Wait, number 2 is value 1. Index 2 is value. Let's try index 3. We are expecting an answer 2. So for which we come back again. By the time we come here, initially for the 3, right? So 3, initially when we come here, the previous value is 0, current value is 1. We get into the for loop for 2, 0 and 1, for loop for 2. We get temp is equal to previous. Okay, 0. Now, previous is equal to current, which is 1. Same thing as before. Current is equal to 1 plus 0, that's equal to 1. So we come back out again when we're coming for I is equal to 3. This whole thing is for 3. This is I is equal to 0 is done. I is equal to 2 is done. I is equal to 3. The value of temp is the previous. So value of temp is previous. Wait, where did temp go?
Yeah, even I am confused
All
myself
right,
now.
that's fine. Okay, let me give you a simple solution. Okay, so this was a good
Okay.
try. This is definitely a good try. This is little. This is exactly the answer, very close to it. But
Yeah, something
what
is
you
wrong.
can do is, I know. So that's just simple. Now this is like a little trick if you want to memorize. Like
Mm.
so, you're going to say C is equal to previous plus current. I'm just even going to go out. Out equals to previous plus current. Okay. Now previous is equal to current, and current is equal to out. Let's see if that works. Okay. So we come back here. We don't have a temp. We call it out. New value though, out. When we come in, the very first time when we come in, previous is 0, current is 1, so out's value is 1. Okay. Previous's value is current. Let's come in, right? When we come before the for loop, everything is 0. 0, previous is 0, current is 1. Now we are getting into the for loop. The for loop is, erase that here. For loop, remember this is for n is equal to 2. When n is equal to 2, we come here. The first thing we do is out is previous plus current. So the out is 1. Previous is equal to current. So previous becomes 1. Current is equal to out. Okay. And what do you return? We return out. Okay. So that's good. So we are returning out, and this is the expected value, which is if you go back, the element at 2 is supposed to have the number 1. Okay, cool. So now let's see element at index 3. So when we come in, this is the initial part where I is equal to 0. So here is we are doing the same thing again. Previous is 0, current is 1, out is 0. out is previous plus current. So out immediately becomes 1. Previous becomes current 1, and current becomes 1. Okay. So next we get into the next for loop. Starting with I is equal to 2 was what we saw here. Now I is equal to 3. We come in. What is the value of out? Ours is previous plus current. That's 1 plus 1 equals to 2. Previous is current. Previous is current. So previous becomes 1 and current becomes 2. Right? So the return value is going to be my out value, which in this case is again 2. Okay, I think we are in a good shape, right? So next time we come in with, let's say for 4, you come in for 4, it will add 2 plus 1, 3. Yeah, perfect. Okay. Where is it? Okay, 3, and the next one is, right? So this is what we are expecting. We're expecting 2 for this value, and we are done. So remember, at the end of the day, we came up with a very simple solution if you look at it. But if you had said the solution very first time, they would have said, oh, they don't know programming, right? But instead, we made them go through all these things. We showed them recursion, we showed them memoization, we showed them that iteration is better. And we even did something after iteration plus plus, which happens to be a simple program. But if you look at it efficiency-wise, this was 2 power n. We were doing it recursively. This is order of n because all we are doing is going through the cache. Iteration is also order of n, and this is also order of n. Right? So we are showing that we know how to start from a very complex solution and optimize it systematically. And that is all dynamic programming is. So having said that, today, I wanted to do something which all the professors say never do, which is try to solve a problem on the fly without trying it. But I wanted to do it and see if I can, all of us are going to try it together. So we'll see how we get to that. The problem is, let's go to Geeks for Geeks. Hey, Chris, didn't see you come in. I guess this is a virtual world. You don't hear anybody come in. We go to algorithms, click on dynamic programming, fall down. And this problem, we briefly mentioned it last time, which is called counting ways to reach nth stair. The question is like this. A child is running up a staircase with n steps and can hop either 1 step, 2 steps, or 3 steps at a time. Implement a method to count how many possible ways a child can run up the stairs. Okay, the input is 4, which means the total number of steps is 4. And the answer should be 7 because it can be, the child can take 1, 1, 1, 1, 1 step, then do 2 and 1, 2, 1, 1, 1, 1, 2, 2, 2, 3, 1, 1, 3. Right? So if input is 3, the output is 4. So as you can see, even here in Geeks for Geeks, they use exactly the same idea, which let's not look at the answer yet. They start with a recursive method and then they add memoization, which is technically called dynamic programming, right? So let's go back to trying this out ourselves. Share this time, this one, content. Not share when somebody else is sharing. Oh, Chris, you're saying something. Sorry. Stores all of the values up for fib up to n correct, right? Yeah. So okay, let me look at your question and go back to. Okay, so let me go share content, screen. All right, say that again, share content screen. All right, so let me ask what Chris, look at Chris's question was. Yeah, okay. Okay, the memorization route, by the way, it's memoization, not memorization. Route stores all of the values for fib up to n, correct? Yes, let's go back to when we were doing a memorization, memoization. Let me write it down to be clear. Memoization. Basically, we are using a memo or a data store. In this case, it happens to be an array, right? So yeah, so see what we are doing. We initialized, let's use a different color. Okay. So we initialized a cache in this solution. This is what we called optimization solution 2. We initialized a cache with 100 values. Then we filled it with -1. Then we decided let's add a new system.out.println. Because if it's an error, we just want to add all our edge cases here. And we are now just going to say fib of 0 or fib of the function, whatever n value is. We initialize the first two values with 0 and 1. And int I is equal to 0, I less than n. So yes, all we are doing now is from 2, value of 2 is the sum of I minus 1 and I minus 2. So 2's value is 1 plus 0, 1. And we keep doing that. If let's say if your n was 3, we keep filling this up, we keep filling it up. When it reaches 3, we stop. And it's just like I said, less or equal to. And now all we return is cache of n, which in short is cache of 3, which is, or whatever value it has, cache of 4, we return this guy, right? So short answer, the memoization route stores all the values of fib up to n, right? That is the optimization which we saw today, which is, let's take out even the storage. So now, oh yeah, so fib, we said this was order of 2n, but remember, we haven't talked about the space complexity. So in the first case is, so this is your time complexity. Even if you look at the space complexity, just do this, right? So this is the optimization. Remember, we did space complexity. In the first case, it's so much exactly the same 2 power n because we are creating new stack frames every time. I really need to work on my whiteboard skills. So here, second time, even the space is only order of n, we have an array of size order of n. Iteration, we still are using order of n, but remember here, we are not even using an extra space. So that is why it's called optimization. All right, let's go back to our question. And I'll post the link to the question in the chat window if you want to pull up the exact question. Window here. The question is, a child is running up a staircase. Okay, so even before that, let's do our standard steps. What is step 1? What is step 1 of solving any problem?
Using recursion?
Nope.
Oh, paraphrase.
Correct. So we rewrite this in our own terms, paraphrase it. Second step is, what is the second step? Okay, core logic. Then we did a dry run. Then we do a dry run usually. And then we do the online editor test. So in dynamic programming, we start with recursion, then we add memoization, then we add iteration, and we can stop there, unless in this particular case, we can think of some other optimization. Oh yeah, edge cases, sorry. Edge cases was, I think we added here. So it's 2.5, my bad. So let's do it clean. Right, you're right, good point. See, even I am not perfect, and that's important. 3, let's call it the pen. So we think of edge cases because null cases will be taken care of inside here, right? Null checks, basically your exit conditions, edge or null, again, doesn't matter. Maybe I'm getting the terminology wrong, but you know what I mean. So 4 is your dry run, and then we are going to use an online editor and try if that works. So let's now go back to our question. The question is, there is a staircase, and the kid is trying to get to the top because the kid's standing here. The kid wants to get to, let's say, step 1, step 2, step 3, and he wants to get to 4. He's only allowed to take 1 step at a time, 2 steps at a time, or 3 steps at a time. He's not allowed to take 4 steps at a time. So if you think about it, the ways this kid can reach is Remember, there's a number of ways. So this is something you should keep remembering. Number of ways not equal to number of steps. In this case, you should be very, very clear about it, because this will eventually confuse you if you start opening recursion up, which itself is a bad thing. But if you end up doing it, this is what you should remember. So in the first case, let's call it A. The kid decides, I'm going to take one step at a time. 1, 2, here. Where does this 1, 2? I'll just call it is standing at 0. Okay. So now, one way is he's doing 1 plus 1 plus 1 plus 1. That is 4. Step A. That is 1, 1, 1, 1, 1. B. So how many ways have we seen so far?
One way.
One way. Perfect. The next step is he can do 1. He decides, okay, I'm going to just take 1 here, but I'm going to skip 2. I'm going to go here. And now from here, I'm going to take 1 more step. So that's your 1, 2, 1. That's number of ways is 2. C is 2, 1, 1. D is 1, 1, 2. What else can we have? We can have, can you tell me what else is left?
2, 2.
2, 2. Okay. 2 more. Two more combinations are missing. Remember, we haven't used 3 yet, 3 at a time.
3, 1.
Yeah,
1,
so
3.
it decides I'm going to jump here, 3, and then it's 3, 1, and maybe she says, I'll do 1 first and then jump at 3. Right? So we have 3, 1, and 1, 3, and that brings us 5, 6, 7 as total number of steps as 7. So our goal is input is 4, our output should be 7. Okay. So now we are together going to start writing solution 0, which is recursion. Okay. Now in recursion, remember there are a couple of steps we even call specifically for recursion. Press something, press something. Should divide that into lecture 2 and stuff. Just 3. All right, it just erased everything we wrote so far. Very smart. So might as well, and I think that's recorded anyway, right? So I'm just gonna, maybe it's a good thing, right? Because we never talked about adding recursion here, the steps in recursion. So let's talk about that, right? So if I tell you this is, what are the steps usually what we do in recursion?
Assume all the steps are taken care of before me.
That's 2.
Okay.
One is, what is one? Step 1. Step
Edge
1 is we
cases.
write a signature.
Signature.
Second one is me, my, previous, which is what you said initially, which is if I am standing in the middle and assume everybody before me is done, then we talk about the exit condition. And there's one thing we do when we leave. What is it?
Return.
Yeah, and how do you write return? No, edge case is taken care of here. I call it exit, edge, whatever.
Okay.
When you have doubt like this, right? When you have questions in your mind, always go back to your very first example. Factorial int n. So we wrote a signature, remember? Public static int. Very first thing, remember. So you can always, this is why I'm teaching you from basics, so that you can always work it back to the foundations and your brain will pick it back up. Factorial of 4 is equal to 4 times 3 times 2 times 1. And we wrote a signature. And second step is if I am 3 and somebody tells me, hey, here's a value called x, which is a product of the people before you, what will you do? We say me is equal to X star me, right? So in other words, we call it, let's do it this way. The output is equal to me star X. And the way we write me is, it's the same value. We're talking about n star something X. So we leave the X as it is now, right? We don't touch it. Now we go to step 3, which is the exit condition. So imagine we're going down, down, down from 4. Our exit condition is if n less than or equal to 1, we just return 1. Especially since it's multiplication, we want to return 1 and not 0. So now this is done, signature is done, me, my previous story is done, exit is done. What is the last step we do?
We return the output only, right?
Okay, so you're saying if I do return out, this is enough?
I mean, you're not calling the factorial method.
Exactly. So that one is what we call parting shot. And parting shot, if you remember, I keep telling you, never think about it. All you do is copy paste exactly the name of the function, factorial. And then what do we do?
I have the previous result, so n minus 1.
Perfect, that's it. So usually if it was in linked list, we would call n dot next. In numbers, we are calling it n dot n minus 1. And now we are done. Right? This is as easy as writing factorial. So let's go back to our case, steps. Right? I think I'm just going to draw the step thing again, just for us to keep in mind. We can use 1, 2, and 3 steps. And we know if the input is 4, we want the output as 7. And 7 is, remember, number of ways and not equal to number of steps. Okay, so let's start with step 1, which is let's write the function signature. Public static. What do I want to return? I want to return the number of steps. So I'm pretty confident this is int. And then let's call number of ways. And we are taking an input int n, which is the value here, n. Okay. Now we are done with step 1. Second step is me and my previous. Okay, so the idea here is, remember the Fibonacci series? To get to 4, what did we do? To get fib of 4, what did we do?
Fib of 4 minus 1 and 4 minus 2. We added
Correct.
it.
We added fib of 3 plus 2. But we added 2 of your children because fib is created by adding things. But in this case, let's put it this way. 0 and the child is standing at 0. We have a child, clearly terrible at drawing. So we have step 1, eraser. We are calling that step 1 again. 1, 2, 3, and 4. Now, can I say after the person has reached here, can I say this is basically just before coming here, let's say the person was at 2, right? Even at 3, right? So when the person was at 3, how many ways can he get from 3 to 4?
One way.
One way. Okay, so there's one way. So can I say that, so I'm not even thinking anything below it. Can I say that if somebody told me that the value, the number of ways to get to 3 is already given as x. Remember, number of ways. It's taking only one step. That's okay. But can I say that once you know what the x value of 3 is, and now we also know the number of ways to get to 2, let's call it y, what will be the number of ways to get to 4? let me even make it more simpler, right? Let's use 2 numbers instead of 3. Just gonna have, we have child is standing outside at 0, 1 step, 2 steps, okay? How many ways are there to get to 2?
Using how many, like which step?
Okay, yeah, sorry. You can use 1 step and 2 step at a time.
No, like, so you asked how many number of
How
ways
many
to reach?
ways to reach to 2, or even let's make it number of ways to reach 3, right?
Okay.
Now let's open it out again. You can do 1, 1, 1. What else?
1, 2, 1.
1, 2, 1.
1, 1, 2. No, so okay.
1, 1.
No.
Just 1,
1
2, right?
and just 1, 2, yes.
1,
And the
2.
previous one is also wrong. B is
We
also
can
wrong.
sorry, this 3B is wrong. It's only 1, 2. We already wrote 1, 2 in that case, so we don't need this. We just need 2, 1 also, right? Anything else I have to add? No. So let me ask this question. Imagine the person is already here. How many ways does he have to get to 3?
1 way.
1 way, which is exactly 1 step. Okay, way, step, difference. So can I say that somebody told me that there are X ways to get to 2? What are the X ways? Actually, in reality, the number of ways to get to 2 is is 1, 1, and 2. There are 2 ways, right? So don't worry about that. But somebody told me there are 2 ways to get there. From there, how many ways do I have?
+1.
Just 1. So essentially, you are exactly here. From here, you don't have a choice. You are exactly you have 1 way. Let's say you are standing here, and I am saying you can go to 3, and somebody tells you you've done everything so far from 1. So how many ways can I go there?
2 ways.
Okay, good. So now let's think about this logic, right? So let's go back to our original thing, and we say, let's start thinking is, going back to our original question, I'm going to erase all this. Oh, no. Yeah, okay, never mind. So there are, when I said number of steps, so there are from 1 and 2, the person can, if the person is here, he can either, to get to directly to 3, there's only 1 way, which is the 2-step one again. From 2, there's only 1 way to get to 3, which is a 1-step, right? So if I tell you the number of ways to get to y is x, the number of ways to get to 2 is x, and number of ways to get to y is 1, the total number of ways to get to 3 is x plus y. Is that correct? So you have only 2 options. Like when you are at 3, you could have come from 1 step before you or 2 steps before you. Let me
Can you
write it
repeat
again.
once?
Yes. Let's start from scratch again. This got complicated. So mere fact that we are already opening this up into recursion is saying we are going down a rabbit hole. We should not do it finally. But for sake of an argument, I'm just trying to make this point here. Just open. Okay, so let's say a person is here. Where all could he have reached here from? Can I say he could have just the penultimate step? So this is the last step. He's already reached 3. Can I say he could come either from 2 or he could come from 1? And like, remember, in this is the same case, we are saying this person is allowed to take only 2 steps at a time, right? And all I'm saying is from 1, the person can, from here, he can just make, to get 3, he can take 2 steps, not number of ways. From here, he can take 1 step. So now can I say that if the person reaches the penultimate step, he has only one way to go. If the person has reached 1 or 2, he has only one way to go to get to 3 immediately, which is the ones we said, whether the person, if he's at 1, he can either take a step to 2 directly, or he can step up to step. That is the only way a person from 1 can go to 3. And that is the only way a person can, one way from person who's already on 2 could have reached 3. Right? So there's only these 2 ways to get here. So
That
the number of,
sorry, I have one doubt.
okay.
So that 2 on the arrow is the number of ways or number of steps?
In this case, it's just a one step of size 2.
Yes, okay.
Okay. Even this one is one step from 2 to 3 of size 1. Okay.
Okay, and even Christopher has a doubt in the chat.
Yeah, so this is Christopher's question is, are we allowed to jump 0 to 3? So in this particular example, we are just doing 1 and 2. So my goal was, let's do 3, right? 1, 2, 3. Just expanding it to the next one. So 1, 2, 3. If a person is here, reached here, he could have either come from just the base, right? The person was at 0. So the kid was here at 0. From 0, he could have taken, from 0, how can he get to 3 immediately in one step? It takes one big 3, right? How did you reach 3? Or the person was maybe at 2, he took one step. Person was at 1, he took a step of size 2. Here, let me rewrite this again. How many ways could a person reach 3 with the given fact that the size of the step can be 1, 2, or 3? The fact is, he could have reached just before reaching 3. I'm not even talking about like starting from 0. I'm just saying only at the last time, the very last time, just before getting to 3, where all could he have come from? He could have come from here and then taken a step of size 1. From 2, he was standing there, he could have taken a step of size 2. And from 1 or 0, he could have taken from step of size 3. Right? My point is, if you know the number of steps by which you already got to the previous ones, then you have only one way out. You have only one way out, which is to reach to 3, which is just take one big step. So if I have 1 ways to get to 1, 2 ways to get XY, so 3 was a bad example. Okay. If I tell you there are X ways to get to 1, Y ways to get to 2, Y ways to get to 3, Z ways to get to 3. Can I say to get to 4, it's sum of all that? The number of ways. Remember, I'm not talking a number of steps. Just, okay, bear with me for now, right? Let's assume that what I said is correct, and I'll tell you why. So let's go back to we just made the biggest mistake in recursion world, which is never open up and think about it. That is, I allowed you to do that, or I let us do that because we wanted to understand the question. But now, all I'm trying to say here is, let's write the function directly, right? You should not think about recursion ever. Public static. This is what happens if you think about recursion. Int number of ways, int n. We wrote this. Say I am as a person in the middle. Can I say that me is equal to number of ways to, remember, in this case, we are allowed to take only 1 step, 2 steps, 3 steps. If somebody tells me the number of ways to get to, so here, let's say we are making this example, right? So 1, 2, 3, 4, standing here. Somebody tells me there are 5 ways to get to 3, and there are 6 ways to get to, number of ways to get to 2, and 5 ways, 6 ways to get to 2, and number of ways of 1 is 3. the point is, once a person reaches any of these penultimate steps, he has only one way to go, right? So his way is stopped. His way is exactly one now. Now, all you have to do is sum them all up, because the number of ways of getting to 3 plus number of ways of getting to 2 plus number of ways of getting to 1 are your. So all we are doing is we are thinking backwards and saying, oh, how did I get here from? This is exactly like your Fibonacci series. If you think about it as fib of 4 is equal to fib of 3 plus fib of 2. And we should never have opened this up. That's all it happened. Right? The moment you open it up and try to understand recursion, you go to hell.
Where
That's
did
it.
the +1 go?
Remember the +1, what do you mean by +1? Number of ways to get to 1?
Like, for example, we were at 3.
Mm-hmm.
So we did number of ways to get to 3 plus 1
Why?
is equal to
+1 is the number of steps, remember?
number. Yeah,
+1 is
number.
the step you are taking. You took step of size 1, but the way from 3, how many ways can you get to 4? Only one way. This is your one step. If you're in the penultimate step, you have only one way to get there. So this, my point is that until your parent, there were multiple ways. But once you reach your parent, the parent could be 3, parent could be 2, parent could be 1. Then there's only one step to get to 4. Step, yes, right? But then the way is exactly the same. So number of ways you get somehow, you get like 100 ways to get to 1, another 100 ways to get to 2, another 100 ways to get to your penultimate thing. Now all you do is one way, which is take a step, could be of size 1, could be of size 2, could be of size 3. So this is going to need you to like sit and meditate or think about this a little bit, which is why I was saying don't never open up recursion. We should do the solution this way, right? So we added me is this, then don't think about it, just blindly write it if n less than or equal to 1, or sorry, 3. So in this case, actually what we should do is we are thinking of, we are going backwards from 4. So we are going to hit if n equal to 0, we're going to say return 1. And we can, yeah, that's fine for now. So else return number of ways to 3, number of ways to 2, number of ways to 1. I know this doesn't intuitively make sense, but more importantly, we need to get the code working even before you start thinking, right? So let's now start thinking, because we just wrote the core logic. What was the step? The step was we did the signature, we did who, if I'm me and my previous ones are told to me, and I thought of an edge case or exit case, sorry, where we are hitting 0 and we are saying, oh, we're going to return 1, which is when you're at 0, you have only one step to take to get to 1, right? So you want the answer to be 0 there. And now we already wrote the parting short, which is just copy the same function, but add to it, my child, my younger child, the child, my return my child before me. So in this case, it's not 3, 2, and 1. It'll be the 3, 2, 1 example was for 4. So in generally, we will be doing n minus 1, which is when I was at 4, how many ways can I get to 3? N minus 2, how many ways to get to 2? N minus 3, which is how many ways can I get to 1? Now, the proof is in the pudding. Let's start trying it with a dry run. So the dry run question was, if I give you 4, can you give me 7? Is that right? What was the output they said? If it's 4, the output should have been 7, right? So let's try opening this up. So we start with n is equal to 4. N is equal to 4. We go back into the function first time. Is n is equal to 0? No. Now we're going to return number of ways of num of ways of 4 minus 1, 3, plus num of ways of 2 plus n, or I'm just going to call it n of 1. Right, so that's it. We finished with the first stack frame. Next stack frame is starting with number of ways of 3. When we come back here, is 3, 4? Is this none? No. Okay, number of ways of 3 is equal to n of n minus 1, 2 plus n minus 2 plus n of 1 plus n of 0. Okay, and here in the stack frame, let's say we take n of 0. We come back here. It says, oh, 1. Okay, this is correct. So I'm going to return 1 here. So number of ways of 3, this one we know is 1. 1, the number of ways is, when we start writing, it'll be 1 minus 1, 0. You actually have to do this too. Minus 1. See, when we did a write run, we just thought it might be minus 1 and minus 2. We must, okay, so when at 1, we want to stop, right? We just can't return only 1. Number of ways of getting to 1 is 1 from 0. But if it's -1 and -2, we should do if n less than 0, we want it to still be returning 0. Because we don't want to add them to the number of ways. I know this is how our brain starts spreading out, because our brain is not created for opening up a recursion, but bear with me. So n of 1 is number of ways of n of 0, and we come back to n of 0. Oh, that's 1 here. And number of ways to get to 2 is number of ways. We open this up, it'll be n minus 1, 1, n of 1 plus n of 0 plus n of minus 1. Let's open that clearly again. So 2, 3 was 2, number of ways to get to 2. Number of ways for 3 is number of ways to get to 2, plus number of ways to get to n minus 2, 1, plus number of ways to get to 0. 0, we realize, hit the base case, and it gave you back 1. 1, we opened up, try again. We said n of 1 is equal to n of 0 plus n of minus 1 plus n of minus 2. And we hard-coded, we want zeros there. We are sending only 1. So now there's a 1 coming back here. Now n of 2, we're going to open this up again. We're going to say, oh, n of 2 is n of 2 minus 1, 2 minus 2, which is 0, and 2 minus 3, which is minus 1. So from here, we know n of 0 is 1 step. N of 1, we just did the same calculation here, right? So n of 1, so we're going to reuse it. Remember, this is the reason why we start with recursion and we add memoization. We're going to add 1. So we now know number of ways to get to 2 is 2. And let's quickly do a cross check. There's step 1, step 2. How many ways can I get to 2? Yeah. If I'm allowed to take only 1 and 2 steps, size of 1 and 2, I can either do 1, 1 or just a 2. Done. So yes, we are right. So far, we are right. Okay, this is number of steps to get to 2 is 1. Number of steps to get to 1 is 1. Number of steps to get to 0 is 1. So now, by the time we get here, there's 4. This is for 4. This is for n is equal to 3. Now remember, we came from here for n is equal to 3. And what we have to do is n is equal to 3 plus number of ways of 2 plus number of ways of 1. So 3, we got the answer as 4. 1 second, it's different color. 3, we know the answer is equal to 4. Typically, in actual recursion, this will also open up. But now, for our sake, we're going to go check what the answer here is. Oh, yeah, number of ways to get to 2 is 2. Number of ways to get to 1, we know, is 1. So therefore, the number of ways to get to n of 4 is equal to 4 plus 2 plus 1. That's equal to 7. This is the expected output. So remember, this exercise you should do only once in your lifetime. Even today evening, you should just go, oh yeah, convince yourself that this is right. Next time onwards, you should just do the leap of faith. And you have to trust the instinct and trust the leap of faith. Just write this out, open it up. So your thinking should stop at, to get to me, how many ways can I come from? Remember, to get to fib of 4, we just were thinking about two children. Two children are fib of 2 and fib of 3, n minus 1, n minus 2. But here, remember, we are allowed to take 3 steps. So we are thinking about from our penultimate step, n minus 1, n minus 2, and n minus 3. That's all, right? So these problems, if you look at it, dynamic programming problems, if you look at it top down, sorry, if you look at it bottom up, it's going to mess your brain up. There's no way your brain can open it up, which is why I'm teaching you this simple trick. Like they say, believe in the system. The simple trick is write a signature, my previous, if somebody tells me my previous just before me is done, what can I do? And we add an exit condition. As a parting shot, we do the copy paste the example, which was, remember, factorial of 4 or fib of n minus 1. So if n was 4, the fact we took factorial of 3, and fib of 1 we'll do factorial of fib will be factorial of 3 plus fib of 4. Okay, so I know this is too much to take, but what I want you to do is go back, do 2 things. First, don't even look at all this, just look at the problem, write your recursive solution, and then do the dry run. Because never try to open it up initially. Try to do the dry run yourself, and then you realize, oh yeah, this looks correct, or you might realize the formula has to be slightly modified. Because like I said, the problem is here we might get lost in the weeds between number of ways and number of steps, which is why all the recursive problems are complicated, and this is a way to get out of it. All right, so we allowed only, is there a question here?
No, just thank you. Yeah, this really helped.
Yeah, just take your time. Don't do it immediately. Just go home, give it a couple of hours to settle in, and go try it this way. Like just blindly write the leap of faith and then go backwards, try run. And next week we'll also see another dynamic programming problem, because this is exactly what I want to do. Like connect between dynamic programming and the basic leap of faith. Once you bridge that gap, you will be able to solve anything. Just write it down immediately, and minor changes will show up in dry run, and that's it. All right, guys. Yeah, just try it out. If you are bold enough, you can go to Geeks for Geeks and try the other problems. But I always suggest keep a timer. If you don't get this written down in 5 minutes, always walk out, because this thing recursion internally is a big trap which might get us stuck trying to open it up. So yeah, that's it, guys, for today. Thank you. I'll see you next week, Monday. No, I'm meeting Wednesday at 2 p.m. Bye.